Donc voilà, on est présent pour le Café Scientifique du 6 décembre. Donc, on a le plaisir de recevoir Francesco Ciari, professeur adjoint à la Polytechnique au département de génie civil, qui est accompagné de ses étudiants Oaussim Manout et Nicolas Rodwell. La présentation va être faite en anglais, mais n'hésitez pas à poser des questions dans le chat en français ou à la toute fin. Je vais vous laisser préciser, Francesco, comment vous voulez procéder pour les questions, si c'est durant ou à la fin. Petites annonces avant de débuter. Par contre, c'est organisé par le comité étudiant IVADO. Notre mission, c'est vraiment de partager, d'aider en fait les étudiants qui sont boursiers d'IVADO, mais aussi de partager les domaines d'intelligence numérique à la communauté étudiante en général. Donc, je partageais dans le chat des informations en lien avec le calendrier d'événements qui sont organisés par le comité étudiant, mais aussi par IVADO en soi. Donc, je vous invite à aller voir ça, surtout pour cet hiver, qui va y avoir beaucoup d'événements qui vont être organisés. Donc, vous pourrez aller voir ça par la suite. Donc, je vous cède la parole, Francesco. Merci beaucoup d'être présent pour présenter tout ça. C'est un plaisir de vous avoir avec nous.
Parfait. Bonjour à tout le monde. Merci beaucoup de mon côté pour l'invitation et pour cette opportunité. J'attends que... Voilà. Est-ce que vous voyez bien mon écran? Oui?
Oui, oui.
Oui, ok, parfait. Ok, donc je vais commencer. Donc ça c'est, on sera à trois à présenter. Justement, il y a Oaussim qui en fait n'est plus mon étudiant, mais qui l'était jusqu'à pas longtemps comme postdoc, et Nico qui vont présenter. Donc ça c'est, sorry, I say I have to do it in English, so sorry for that. So this is the outline of the whole presentation for all the three of us. So a short introduction on myself and on my work, then about agent-based simulation, which is the methodology I mainly use in my research, and it's also what is probably most interesting for this audience. Then MATSIM, which is the specific software of agent-based simulation that I'm using. And then it will be a turn of Oaussim with an application on COVID spread. And then Nico with the integration of machine learning techniques into this simulation. Then I will have just a few words at the end as conclusion. All right, very quickly on myself, I did my PhD at ETH Zurich in 2012. I worked afterwards in Switzerland and Austria as a senior researcher and professor at Polytechnique since 2019. My work, so I'm in transportation. So what I'm doing is transportation planning and child behavior. And the topic of most of my studies is on innovative transportation. And the methodology, as I mentioned already, I use most is agent-based simulation. So this is what I will talk about in the next 5 to 10 minutes probably. Now, just a few words before I start going into the topic. There are things I will go rather quickly, but I have a bit more. So in the slides, there is a bit more than what I will say for your reference. I don't think there is time today to really go into the details of the whole thing. I mean, something you can have a full class on that, but for your reference, there is a little bit more in there, and then, well, you can always answer to questions. So this is an example I will go through very quickly. So what's a simulation? First of all, it's something where we recreate a model of the system we wanted to analyze, and in a way that we try to approximate its behavior. And we do this when we are not able, or it's not very practical to use mathematical models to represent the system, which is something very often otherwise. So when you don't have, for example, analytical solutions or is not practical, as I say, you go for simulations. Well, agent-based simulation, what is an agent? An agent represents an individual, has a set of attributes and characteristics. So it's like a piece of software, but which represents an individual of the system, follows given behavioral rules, has decision-making capability, has a goal. So you want to achieve something. He acts in an environment and interacts with the other agents that are in this same environment, is autonomous and can learn. And agents can also be heterogeneous, and their attributes can change dynamically. And this is a definition that is kind of a reference definition in computer science. Now, in transportation, we tend to be a bit more minimalistic. I will explain a little bit more later on that. So here, just to visualize all this, so we have a single agent with all the items I just mentioned. So we have an artificial environment, and when I say artificial, is everything obviously in silico. So it's a computer software, and we have agents interacting among them according to certain rules, and they can be agents with different kind and with different goals, also respecting different rules, etc., etc. But the main idea of agent-based simulation is we do represent the actors of a real system, and at the individual level, and they implement simple rules. And then the behavior of the system is not explicitly modeled, but emerges from the simulation. Meaning that simple rules implemented at the micro level, individual level, allows modeling complex behavior at the macro level, so at the system level. Complex is important. There's also a complex system, what we generally will try to model in agent-based simulation. And the definition of a complex system is a system which is governed by rules that, if you know the rules, you're not supposed to understand the function of the system as a whole just by the rules. So it's, and that's what complexity is. What are pros and cons of such an approach? Well, it models individuals, which is easier to understand in a way, so to interpret also. You have the possibility to have heterogeneity. You have this emergent behavior I was talking about, and you can inherently deal with complexity. On the other side, on the flip side of it, you need a lot of data. You need skilled users. And you have high computation time. And why this is becoming more and more popular in transportation? Well, because the transportation system is becoming increasingly complex, and exactly because the kind of things I'm looking at, like innovative transportation modes. So if you think at right now and 20 years ago, or a bit more, even more difference, well, you have a lot of things that didn't exist, and we expect even more. So if I think of all shared mobility instances, if I think in the future, for example, the autonomous vehicles and these kind of things, obviously it all increases the complexity because we have more options, and because individual will need to choose among more options. But on the other hand, we also have increased existence of individual data, and we only need to think at our smartphones that we all have always with us. We have increased computer power, although, well, if somebody of you is familiar with the Moore law, well, it's kind of stopping being valid, but nevertheless, for now, we have still increasingly computer power for the same amount of money. And well, the last thing is something really interesting for you because it's really specific to transportation. But, all right, so now this is agent-based modeling in general, and why it is interesting in transportation. Then Matsim is the specific software I'm using. I helped developing when I was in Zurich. So it's multi-agent transport simulation. At a glance, it's an open source framework written in Java under a GNU license. It's a huge academic project that started over 15 years ago. And as I mentioned, it's developed at ETH Zurich and TU Berlin. If you want to go look at the website, it is there. But I start with this. So this is a visualization of the simulation. And I think you can recognize the island of Montreal. So here, obviously, are the vehicles moving around. And according to different time of the day, you have different situation on the road network. Obviously, then starts over. So this is what you see is the morning peak. When you have red, it means that circulation, there is congestion basically. When you see just green, it means that it's so vehicles are moving at free flow speed, more or less. But you know, this can be impressive or not. I mean, the visualization is nice, but what is interesting to point out is all what you see here are agents moving according to their needs and trying to fulfill their goals, the daily goals. And this is something that represents the equilibrium in the system. And I will explain why equilibrium and what it means in a second. But I just wanted to start with if you want, from the end, so the final representation of it. Now, MATSIM works in a loop. So why? Because, and that's where this equilibrium thing comes from. We have an initial transportation demand that is, well, our input, if you want, meaning every individual has his daily plans, where they want to go and when, and also initial attribution of modes and routes to go to fulfill these plans. Then there is a physical simulation, and the visualization you have just seen is a representation of this physical simulation of movements of the vehicles, which is queue-based, not going into details there. But the main idea behind the whole simulation is very simple. And you remember when I was defining agent-based simulations, I said simple rules implemented at individual level gives us a complex behavior at the system one. So the rule here, the main rule is really a positive score for the agents for activities. So that's what you want to do. It's not travel per se, what you want to do, but you want to go somewhere for work, for leisure, for buying something, whatever you might need to do. And this is what gives you utility, if you want to use an econometric term, a negative score for travel. But then, and then you have to see this as a sort of giant genetic algorithm machine. So then every individual can change the characteristics of their day. So, and they can change along a few dimensions. So the time they are doing certain activities, the route, the mode, and also the location for certain activities. Obviously not for work, this is fixed. But for example, if I go shopping, I can do this at different locations. And then the intelligence of the system is, or part of it is that they can remember good plans, and they try to adjust according to this memory of what is good. And consider that two things. One is the way it works is similar to a concept that probably some of you are familiar with, and Nico later will mention explicitly, which is reinforced learning. And the other thing is that the system as a whole is usually considered as a form of artificial intelligence. I mean, the intelligence of the single agents is rather very limited, but as a system, there is this emergent behavior, which is, if you want, a manifestation of the intelligence of the system. All right. Oops. Okay, so for an agent's staying point, what we have is that I have a plan with certain characteristics. I try to implement this plan, and this is one iteration. So I go on the network, I do realize my plan, and then according to what happens, I give it a score based on my utility function. And then, well, according to how it went, I give it a score, and I keep it in my memory. And then I try again and again, and sometimes goes better, sometimes goes worse. And I tend to keep what goes better and tend to discard what goes worse. But as I was saying, the point is not, so at this point, it might look really as reinforced learning, but here is different. So here is really the co-evolution, so with the whole population of agents. And then we will have this evolution, and obviously I say obviously because in the end, since everyone is doing for him or herself, we don't have a perfect optimum, in the sense we don't have a system optimum. We have what we call, so it's a Nash equilibrium, basically a user equilibrium. All right, and this is, I'm not going to the detail here, but basically at the general level, we have an equilibrium, meaning we don't have, so the total score of the system is not changing anymore. All right, so this is the simulation we have. I know it was rather quick, but I hope you could get at least the main idea of it. And just very, very quickly before I give it to Oaussim. So here you have a timeline, and it's not the kind of slides you should probably present. So you're not really supposed to read all this, although if you're interested, there are interesting references. But here the point is, when I started with my dissertation, we started really with a conceptual word. You can see in the red, the part in red at the top left. And then we went with more and more details, most of the time on, as I said before, in innovative transportation systems. So going really through giving more and more detail, and then really looking at policies. So, and basically it reflects the growth of the simulation and the possibility given by the simulation. And the very end is what Oaussim will present. Well, part of it, which is an application to the COVID-19 pandemic, because basically, what we are simulating is kind of the flow of life of individual, although in a very simple way. And then obviously we can also represent contexts among people, and then obviously this is relevant in the context of a pandemic spread. Before I give it to Oaussim, I think it's the last one. So on the current work I have, there are some examples here, co-simulation of electric vehicles and the power grids, the impact of autonomous vehicles in Montreal, optimization of car sharing operations, a coupling of life cycle assessment with agent-based modeling, and the calibration of MATSIM with machine learning. So those are all current topics. I have a few more coming soon, but that just, I just want to give a general picture. All right, this is on my side for the moment. I have a few final notes, but I will stop sharing my screen. I don't know if you have a few questions already. I'm fine with it. Otherwise, I give it to Oaussim, and then we can have all the questions in the end. All right, I assume it's fine. So I think Oaussim can start sharing.
Okay. Let me share my screen and tell me if it's good for you. You can see my screen, the full one. Okay, can you see my screen? Can anyone please confirm? Okay, okay. Merci. Thanks everyone. Thank you for the invitation and the opportunity to present this research work conducted with Francesco Ciari on agent-based modeling on mobility and especially on COVID-19 in Montreal. I'm Oaussim Manout, a researcher at the University of Lyon in France. I mainly work on mobility and activity behavior and simulation. And this work was conducted when I was a postdoc working under the supervision of Francesco and in Polytechnique. So let me go straight to the point and say, why would a researcher working on mobility and activity of people be interested in COVID-19? And I think that all of you will agree if I say that daily activities and the mobility of people is critical to the spread of the virus. On one hand, the physical interaction involved by daily activities like, take for example, work or leisure activities, help transmit the virus from one individual to another, and the spatial distribution of activities. So people live more or less remote from their work, and the facts of traveling from one place to another help also transmit the virus and propagate the virus from one place to another. So what we advocate here is that to control COVID-19, it is critical at least to understand how daily activities and the mobility of people help transmit the virus. So this research question is not new for infectious diseases. So research has already underlined the role of mobility and in the spread of infectious diseases, whether it be at the continental, national, or urban level. But the new thing here is that we also put a focus on the daily activities. So the research question of this work was how daily activities, their distribution in space and time, and the characteristics of the individuals involved in them help contribute to the current COVID-19 pandemic. And we will work on the specific case of Montreal. So to do that, to tackle this question, we rely on computer simulation, and especially we rely on two agent-based models. So there is the MATSIM model that Francesco has just presented. It is a mobility simulation framework that is based on activities and on agents. The new added model or simulation framework here is EPISIM, which is for epidemiological epidemic simulation. And we rely on various data sources to simulate how COVID-19 the SARS-CoV-2 transmits, propagates in the population, and we observe the emergent infection dynamics. And now you understand why are we talking about emergence, since we only model the individual behavior and we try to find out how this replicates on the global level. So, okay. EPISIM is a model developed by the same, one of the two teams that have developed MATSIM, and it is like two submodels. MATSIM is a propagation model. Propagation meaning how the virus can propagate or how agents can infect each others. So the way we model this is simple. We assume that the probability that an agent A infects agent B is just a function of the risk. And the risk is a function of the duration of the interaction between the two agents, the intensity of the contact between the two agents, meaning if the agents know well each other's, they will be, or they are too close to each other physically, the risk is higher. And it's also dependent on the fact that if agents A or B are wearing a mask. So theta is a parameter that we calibrate in order to replicate the data we observe in Montreal. We can use data on the number of infections. If these data are reliable, we can also use hospitalizations or any other data related to COVID-19. So this is the main like individual formula we use. We calibrate the theta parameter, and in each time an agent is infected, EPSIM can also track the disease status in the agents, meaning how the disease evolves. And we use for that like a chaining rule to see if the agents will recover, will get seriously sick or critically sick. And to do that, we use the some time-dependent probabilities or some, let's say, stochastic rules. And all of these rules and probabilities are are taken from the data from Quebec and Montreal. So we know that agents start to present symptoms like around 3.5 days, given a standard deviation. Maybe 20% of them will get asymptomatic. And if they can show symptoms, maybe some of them will get seriously sick, or some of these seriously sick will get critically sick. And for that, we use an age-dependent models, meaning that older people will have more chances to become critically sick than younger ones, and so on. So all of this is taken from the data from Quebec and from Montreal. So this is what we call the progression model of EPSIM. So I've said that we work on the case study of Montreal, and we specifically work on the census metropolitan area of Montreal, which like compounds 4 million of inhabitants and around 82 municipalities. For that, we define a synthetic population, meaning that we reconstruct the population of the CMA of Montreal, along with their characteristics, the age, gender, where they work, what they do for their during the day, a normal, conventional day, how long which travel mode they take to go to work or to go to leisure, which leisure activities do they perform, and so on, so on, so on. So one important point to stress here is that we simulate a business as usual scenario, meaning that we do not consider health mitigation measures, the ones introduced by Logo and so on. We consider that people have not changed their behavior and that there is no vaccines right now. There is no vaccines. There is no Omicron variant. There is no other mitigation measures, no curfews as well. So this is, you might tell, too unrealistic assumption, but it is still important and interesting to study this case study, because it can be the case where activities have resumed after the summer break in September. People like have started to have like resumed their activities and start going to work. No remote work was enacted and so on. And this is still an interesting situation to simulate. So we also considered that the start or the onset of the pandemic starts with like 10 randomly chosen agents in the population. So this is the import of the disease from abroad. And we also assume that each agent can at maximum interact with 8 people or 8 other agents. So here are the results. And what we can see is that daily activities contribute unequally to the spread of COVID-19. In 91% of infection cases, we can see that they are due to other home, work, or education. For 41%, 30%, and 20% respectively. Secondary activities like leisure or shopping, contribute less than 6% to the number of infections. And once again, please keep in mind that this is related to the business as usual scenario. This is not the current case of the infection in Montreal, and this is just the simulation results. And we should also say that this distribution follows to some degree the distribution of the time spent in each activity when we analyze the daily plans of Montrealers. So I said that home is the first place where infection occur, and when we track when we try to trace back over 2 levels the origin of the infections, we can see that in 86% of the cases, the virus is introduced from either work or education. So this gives us the idea or make us say that, okay, how in households where there are like 2 or 3 workers, where there are school-aged children, these households should be more vulnerable towards COVID-19. So we computed the empirical infection risk for these households, given the size of the household here and the number of children in the households. And yes, we can see that the probability here, given the color, is higher for households that have 3 kids, for example, and of size 6 persons, and so. The same was also true for if we replace the number of children by the number of workers. And for example, in a household of size 5 with 2 workers and 3 kids, the odds of infection relatively to a non-worker 1-person household are the odds are 87. I also said that work is the second place where infections occur. And we can see that in the top position, the healthcare and social assistance sector is where most of work-related infections occur. So this sector employs like 12% of the population of Montreal, but it is responsible for nearly 17% of the infections. In the second position, we can see that the retail, trade, and the manufacturing comes after that. It is noteworthy that the infection distribution is gender dependent, but this is mainly due to the gender biased job market in Montreal, where, for example, females represent 78% of the workforce of the healthcare sector, or 67% of the educational sector. So also most infection in the construction, manufacturing, or transportation and warehousing are among males, and that's because in these sectors, males are overrepresented. They are more than 50% there. So these discrepancies in the distribution of genders are important to consider when enacting policy interventions. In relative terms, we see that some sectors, this is the healthcare sector here, some sectors are like bear more risk for the workforce of their workers than others. This is the finance, insurance, and leasing. Okay, let me get now to, I was talking about primary activities like work, education. What about secondary activities? So in secondary activities, what we have seen is that in 60% of the infections during shopping or leisure or other activities, we have seen that in 60% of the cases, the infection occurs after 8 p.m. When compared with non-infected agents, infected ones are found to perform more late and then secondary activities. For example, 45% of infected agents finish their secondary activities after 5 p.m. When only 35% of non-infected agents do so. Why is it so? simply because late ending activities are longer. And we know that I've showed you the risk formula that shows that the risk is proportionally dependent on the duration. The higher the duration, the higher the risk. So undulating activities that are that have higher duration or bigger, or people spend more time in these activities and therefore bear more risk of getting infected in these activities. Now that we have shed some light on individual activities and their corresponding infection risk, let me go to the daily plans. Are there some daily plans that are riskier than others? And the first question we asked ourselves is that, what is more riskier? It is many daily activities or longer ones. So one might think that multiplying daily activities, doing like 4 or 5 daily activities, will like increase the risk of infection. And given our simulation results, we see that when we discard the people that do not perform any activity, like retired people in long-term care facilities and so on. When we discard these people, the risk of infection does not depend that much on the number of daily activities. What we have seen, on the other hand, is that infected agents spend more time outside of home than non-infected agents. In average, they spend 1 hour and 45 minutes outside home, which makes them more exposed to the virus. So this is all about the business as usual scenario that I've described, and I've told you that in this scenario, there is no mitigation measures and there is no policy interventions. And in a second scenario, we decided to include massive teleworking in the population, since we know what people do with in the day, and we have decided to impose massive teleworking depending on the economic sector. And what we have observed is that the number of infections in homes increases relatively to the no intervention scenario, and the number of infections in work intuitively decreases since there is teleworking or remote work for home, and also the number of infections in educational facilities also increases. Here I'm talking about the relative distribution. Overall, the risk of infection given teleworking decreases for the whole population. We have conducted a lot of analysis given this second scenario about teleworking. We've seen that this is the decrease in the risk of infection given the economic sector, and this is the rate of teleworking from 5 days a week to 1 day a week. And we can see that the relation is not that linear. There is a decrease in marginal benefits of teleworking, meaning that maybe there is no need to impose 5 days, maybe 3 days are good. Imposing 5 days over 3 days will bring just a minimal marginal benefits given the other costs of teleworking on, I don't know, social and other costs. We also analyzed this scenario given the gender lenses, and we can see that women, or let me put it in another way, men benefits more from teleworking than women. The risk of infection, the relative risk of infection relatively to men increases for women when we impose teleworking. Why is it so? Because women occupy essential jobs. I've said that 78% of the workforce of the healthcare sector are females. We also analyzed the impact of this on the distribution, the spatial distribution of the disease, and we have seen that the central business district of Montreal is where the benefits was the higher from teleworking and so on, and the Quartier Nord, the northern neighborhood, for example, is where the benefits was low. This is a cluster of low reduction in the risk of infection. The same here and here. So let me finish here. Open to your questions and to your comments. Thank you. So yeah, before finishing, there is a paper that we have published on this that includes more details. You can find it here when we will send you the presentation. There is also a working report also that is available. So thanks.
If there are no questions now, I think Nico can go for its own part.
Oh,
Yes.
1 second, let me share my screen. So I am a new student and I am presenting not results, but I guess ideas more. So the name of my presentation is Transferable Transport Simulation. And I think one of the things that wasn't highlighted, or one of the things that, even though Matsum is very good at a lot of different things, it can take a long time to be able to do. And kind of some of the intelligence that is there in the algorithm makes it so that you kind of, whenever you do a new scenario, you always have to start from zero. So one of the things that we are looking at is how to improve the computation time. And one of those things that I've been thinking about is how to be able to go, well, if we did one simulation with a lot of parameters that are similar, how can we get the next simulation to be much more quick? I think Francesco already went through a bunch of these, so let me start here. So these agents, they have a memory of their plans, okay? And then what happens is that the plans that get selected, so usually they have like an amount of plans. So they say, let's say 10 or 20, and says, okay, well, this agent can hold 10 or 20 plans, or 10 or 20 different scenarios that it's able to run through. And then the plan that it selects is based on logit selection probability. So depending on the score, this should be score. So depending on the score that the plan has, then we'll like weight the ones that have the highest score, and they'll be most likely to be selected. And then when all the plans are selected, then we do this physical simulation again. And this process iterates over and over again. But it's a co-evolutionary algorithm. And what that means is the agents optimize their own utility. They're kind of battling between themselves for space on the different roads, on the different transport networks, whatever that may be. And the iteration of this process finishes when the average utility over the agent stabilizes. And I think what's really important to like kind of show here is that this isn't like the algorithm doesn't optimize overall traffic flow. All the agents fight each other. And then once we've iterated enough times, then kind of the average utility will stabilize. And that's kind of the idea of a lot of this MATSIM simulation. And just to highlight how this is slightly different than what is called like reinforcement learning. So reinforcement learning is also agent-based. And kind of the, I think, easiest distillation of this is this very simple little comic here, right? So it's like you have an agent, and then it has an environment. It looks at the environment and then selects an action using this thing called a policy. And the policy is really the important thing in reinforcement learning. It's the thing that like, it's kind of the little mind of the agent. It says, okay, well, I have the state of where I am. I need to figure out what I want to do. So at the beginning, usually you kind of like initialize at like a dumb, policy. So they don't know what to do and they need to learn by examples. And that's the algorithm. So, okay, so now he goes and he touches the fire and he gets minus 50 points, right? So then now he knows, okay, well, over many experiences, it'll be like, okay, well, fire is bad, water good, kind of thing. And then so we're going to update the policy and say, okay, well, once I see this, when I'm in this state and I go to work and I take this action and I go towards the fire, then I'll get a negative reward. And then I'll keep on iterating this until here what's called the optimal policy. So the optimal policy here is just like, what are the things that optimize the, usually it's called discounted rewards, so the rewards in the future for this agent. And so the things, right, the policy is kind of is one of the things that are intelligent of this reinforcement learning. And it says, okay, well, I have a state. If I take an action, what are the likely things that will happen? And am I likely to get rewarded or not rewarded in the future? And people have been doing reinforcement learning for traffic simulation for not very long, 2-3 years, it seems, 3-4 years maybe. And it's shown to decrease, for some of the papers I've looked at, it's shown to decrease computation time. And there's kind of two important things. Some of these reinforcement learning systems are built on physical models, which is kind of similar to MATSIM or SUMO. And some of these reinforcement learning are built by sampling trajectories. And I'll discuss the sampling trajectories in a bit and how that's important. So we have this, although we've talked about MATSIM, there's also these different type of simulators. That one of them is called SUMO, and SUMO is not quite as impressive as MATSIM because it assumes that you have already a trajectory for each car, and what we're trying to do is just figure out how long the trajectory will take given every other car, instead of trying to figure out all the different activities and full day things that someone might do. So it is kind of a lower version of traffic simulation. And I think what's important to show here, right, is that for this type of SUMO, for this type of traffic simulator, an RL system was built where it, on a 6x6 grid, which is a very small grid, it has something like 25 times speed up versus this physical simulator. So here they're using a physical model with RL and they're able to get like pretty good results. So, being able to use reinforcement learning to emulate or emulate what MATSIM or SUMO does might be a good way of going about getting the results that we are getting. And then we have something called learning to simulate, which is slightly different, where here, instead of like using a physical model, which this city flow does, we are trying to figure out what the trajectories will be based on sampling the different trajectories in real life or from some other simulation. And once again, this is a paper that is talking about learning to simulate for this simulator called SUMO. And what happens here is that there is an agent and it observes the environment, right? So in reinforcement learning, the most important thing is that they observe the environment. And then after they observe the environment, they take an action. So for this SUMO, it's about where are we going to change speed according to the policy. And then these little guys, they change speeds. And then what we do is we say, okay, now that because we have real trajectories or maybe even simulated trajectories to be able to compare to, then what we want to do is, this policy that we said, do we want to be able to know what's going on? We compare to the expert trajectory. And we figure out, this was very close to what's seen in real life. So we say, it's very similar or it's not very similar. And then we update the policy, this kind of intelligence, based on how similar or dissimilar it is to the real trajectories. So what we're trying to do here is we have already what we think is the real thing. So if it's in Montreal, it could be like a car going down Saint-Denis. I'm saying that because I live on Saint-Denis. And we say that our simulator said, we'll go very fast, but what we see in real life is that it goes kind of slow. And then we update these trajectories according to what the real life has seen, what's in reality. This is not the same as MatSim, where everyone's competing with each other, where the agents themselves are competing. And then there's another one that's like learning to simulate for MatSim. So this is a more involved type of reinforcement learning algorithm. And what happens here is that they sample 10% of trajectories in real life. And here, right, they use an RL system to minimize the total amount of time spent for each agent on the road. So unlike MatSim, where every agent is fighting for space, in this reinforcement learning algorithm, they just tried to minimize the total amount of time spent on the agent on the road. And they used another machine learning algorithm called a neural network as a policy. And what they find is they get very similar results to MatSim. Even though the kind of the objective of the way that it's optimized is quite different, you see here that this is MatSim, average time spent on link. So like how long a specific agent spends on a specific link, compared to this PODEP is the specific type of reinforcement learning algorithm that they use. And it's pretty linear, like there is some noise surrounding it, but you can see that most things follow a quite linear pattern. So even though we use a different objective and a different way to optimize for reinforcement learning, they have shown that they can get quite similar results, which is interesting. Okay, so I think for me, the thing that is like interesting is the thing that I said before, is that for every MatSim simulation is to start from scratch. And that's because I've been thinking about why that is and what it is that's different between reinforcement learning and MatSim. Actually, let me hold on to that thought. So I guess the question that I want to answer is like, can we transfer intelligence from one run to another? And in reinforcement learning, there are lots of different ways to transfer intelligence. We can transfer a policy. We can transfer using demonstrations. So we can like actually use demonstrations from real life or anything else to be able to learn from these demonstrations. We can learn from representation. So I haven't talked about this, but in some reinforcement learning models, you actually try to model the world and you figure out what the model of the world is. And then you can transfer your model of the world. And there is a lot of other things, but I'll just keep it for these three at the moment. And I think, sorry, let me stay here. I think what's important here is that like in MatSim, right, the coevolutionary algorithm is that all of these agents, they have a plan. You select a plan based on the scores, and then you just keep on iterating until you have like a stabilization of what the overall utility is. Here, it's a different concept, right? You have a policy. So the agent is like, okay, I see all of these cars on the road. What should I do? Right? So based on the environment that it sees, it makes a decision. And because it kind of looks at the environment, we can transfer the knowledge of that understanding of the environment and what action to take. Whereas in MatSim, it's just like, okay, we're going to randomly select some plan. And then after we keep on randomly selecting plans until we get a stabilization. And there's no intelligence of which plan was used. But here there is an intelligence of which policy. That is the intelligence itself that we are trying to transfer. And I don't know if, are we doing questions? I think this is the most important part to kind of understand. So if anyone has questions about this, this would be the best time to ask them.
I don't see any question on the chat, so I think you can go on.
Okay. And what's important is that with this transfer learning, you get usually a lot faster convergence to the solution. So, you know, we can have, you can have a scenario A transfer learned on it. You can have a new model trained on the exact same scenario, and you'll get faster initial point and faster convergence. Here, you can also have a scenario A transferred to a different scenario B, and you might not have a faster initial point, but you'll have faster convergence overall. And then finally, you can also have a faster convergence and a better performance on the model. Here, performance is kind of difficult. It's not like we care about. We're not trying to actually make traffic better. We're trying to see what would be the actual result. So performance here would be slightly harder to figure out in this case, but if we talk about the specific types of transfer learning, right, there's learning from demonstrations and actually learning to simulate. So this model here is actually a way of transfer learning in RL. So we're learning from real trajectories, and it's faster to do than other scenarios. So learning to simulate sumo is a type of learning from a demonstration called generative adversarial imitation learning. And that itself is a type of transfer learning which will speed up the process, speed up the computation time. And then we can have this policy reuse. Like what I was saying is that like the policy here is like the decision-making process of the agent. And that's what we want to really give to the new agents. We say, okay, well, we have this decision-making process, take it. It might not be able to use automatically on a new scenario, but we still have a very, very good starting point. And then from that strong starting point, we iterate many less times. And that's where we see like the graph before, where you have a faster convergence to the solution. So conclusion, right? Traffic simulation is important for transplanting and design. Actually, I didn't. These models are actually very computationally expensive and not transferable. RL has shown to reduce computation time. And I think there's a really big opportunity to show that there is further reduction by transferring knowledge between simulations. So maybe not in the first simulation, you might not get the best computational reduction. But if you use that intelligence from that first model for the next 10 models that you use, and they're all much faster, then you get a the ability to simulate many more different scenarios that are slightly different. And that's all I have.
Thank you very much.